Okay, here we go. One note, I guess. I posted the solutions yesterday. Where are they? Oh yeah, here. The practice test. It's time to replace your laugh. No. It's okay. Thank you. Would have been searching that remote forever. Okay, so I posted the solutions. I do want to apologize for just one of the questions because it was a little bit more complicated than I wanted it to be. I had just looked at it and thought, that's a good one. And then when I did the work, well, it was more than 1 mark, that's for dang sure. And but just as a little bit of a legend, I tried, now it's kind of difficult, but I tried to do blue for work that I expect to be shown on the test for full marks. Okay, just so you know kind of the extent of the work that you have to show. Pink is potentially helpful notes, trying to be helpful, I don't know. And then orange is kind of optional work that you don't need to show, but that I find helpful in solving the problem, okay? And so that's kind of the legend that I tried to stick to. Now, where is it? Where is it? Where is it? That little, it was this one. So 5A was more complicated than I wanted it to be. I wanted it to just be plug values in and find the outputs, right? And then find the change of rate. That's easy enough, right? So find the output of the second point, find the output of the first point. Now that's where it got a little bit weird. All those fractions, a lot of work. You can just use your calculator, right? It would just spit out that output. So it's not like you can't handle it. It's just not something that I expected, because then what you're dealing with is a ton of fractions, and we haven't practiced a lot of fractions yet. So that's why I feel bad about that one. And you won't have to do anything like that on the test, but be prepared to do something like B. Oh, that's A. Be prepared to do something like that. No, like B, where you have 5 and 5 plus H as your endpoints, remembering that the H in the denominator always cancels out. I had to use up a little bit more than the page, right? There's always an H left, or usually, but the H in the denominator cancels always. Otherwise, you did something weird. Okay. Any questions about the practice test before we get into chapter 3? No. No, Emily, you said the test is on Wednesday. We're going to study today and tomorrow. And that's your right. That's your right. Any? No?
Well, I can't really load the answer sheet.
Oh, is it not loading? Is anyone else able to get it?
Yeah.
I'm just going through Moodle, but so it should work.
Okay.
But yeah. If not, I can you can send me an email and I can email it to you. Yeah. Because you'll want those. Okay. So we did a little switcheroo by request. And so we're going to do power functions and polynomial functions today, starting chapter 3, which is not on the test, right? So do with that what you will, I guess. And let's see here. That's not the one. I need a new note. Call it. so where was I here? Of course, it's probably not showing off what it's all a surprise what I'm doing, I guess. I'll say test number 1 on Wednesday. Said that so many times now, but it can't hurt, right? All right. So polynomial and rational functions. Have you guys seen polynomials by name before? You've seen them, but you might not have called them polynomials. But I'm wondering if you have done any polynomial work in other classes, maybe? If not, here we go. Okay, so first thing we need to introduce is something called a power function. Now, a power function is exactly what you think it is. It's when you have the same thing being multiplied over and over and over again. So then you can say that x times x times x is the same as x to the power of 3, right? And so that is called a power function. And we've seen power functions already. Make it a little bit bigger. Okay. Where's my pointer? There it is. Okay, so a power function is anything that you can rewrite as x to the power of p, where p is just any number. Okay. And so power functions that we've already seen as part of the toolkit functions, we've seen what? We've seen, all right, in the toolkit functions, we've seen x squared. That's a terrible squared, which generally looks like this, right? A parabola. We've seen x to the power of 3, right? X to the power of 3, which generally looks like what? Whee! Oop. Right? Now, remembering what these shapes are is going to be very helpful in this chapter. Okay, so that's why I'm introducing them again. Okay. What are some other toolkit functions that we've seen that could be rewritten as power functions? Well, where are those toolkits? Where are they? I hope I have them. I don't. Bookmarked. Does anyone remember what section they were introduced in? I feel like it was 1.1. Yeah. Oh, here's some, but it was 1.1. Thank you. They come back to it a lot, but I want the graphs. Here we go. Graphs of the toolkit functions. Maybe not these ones. Well, we can start with these ones. Riddle me this. Are these power functions? Technically, yes. Why? Because if you have something like f of x is equal to 2, now that's a constant, right? So it's just a a horizontal line, that's fine. But what's that the same as? That's the same as times x to the power of 0. Anything to the power of 0 becomes 1, right? And so now you have 2 times 1, right? And so here, this is 2 times 1, which is 2, right? So you could rewrite it as a power function. Same thing here. Oops, I need a longer arrow. Bink. What about f of x is equal to x? Well, probably x to the power of 1, yeah? Usually we don't write the power of 1, but it's still a power, it's just 1. And so, so all these very basic functions are still power functions, but we're more interested in these higher powers, right? Higher powers. Let's have a look at some of the other toolkit functions. Remember, the toolkit functions, they're the ones that we're supposed to know inside and out, what they look like, how they behave, right? So we talked about x squared, x cubed, right? Those are relatively obvious power functions, right? They have that exact form that we introduced, x to the power of p. What about x, the square root of x? Can I rewrite that as a power? You bet. All right. What can I do? I can rewrite this as f of x is equal to x to the 1/2, right? Any root, the nth root, you can rewrite as a power of 1 over n, right? And so here, note, the nth root of x is the same as x to the 1 over n. Now that's a rational, so a fractional power. We're gonna parking lot that for a little bit. We will deal with it, but not right away, okay? But just remember that it is a power function. It's just kind of a weird one, right, with the fraction. What about these guys? Well, we just said that if I have the nth root, I can rewrite this as x to the 1 over n, right? So this I can rewrite as f of x is x to the 1 over 3. Fair enough. What about 1 over x? Still a power function. It's a little bit weird, right? Because what can I do with that denominator, right? I can move it upstairs, is how I like to think of it, by negating the power, right? So here, this is technically 1 over x to the power of 1, right? And so what can I do? What can I do? This is f of x is equal to 1 over x to the power of 1, which is the same as x to the negative 1. I don't remember mentioning that explicitly. It is something that you've probably seen before, but we'll work more with exponents in this chapter. So we'll get used to that. But just as a fact, if you have something in the denominator, you can bring it upstairs by making the power negative, right? And by upstairs, I mean into the numerator. But upstairs is cuter. Bring it upstairs. Same thing, right? 1 over x squared, I can rewrite as just x to the power of negative 2. It's nice when you can see the power, right? But you get used to just recognizing that x is really just x to the power of 1, right? So they're all power functions. Oh, great. We thought we were done with those. Yeah, right. Yeah, right. Let's go back to the ones I want to focus on today are x squared and x to the power of 3. Okay? And the reason for that is because here we have the even powers and here we have the odd powers. And what's useful is that all even powers will look sort of like this. Okay? It'll have this kind of parabolic shape. What happens is as you increase the power, it kind of sits on the x-axis a little bit and becomes tighter. So it just kind of, but the general shape is the same. Okay, and same thing with x to the power of 3. Well, that's going to be the same shape for any odd power. So it'll always look like this, but again, it's going to kind of sit on the x-axis a little bit and tighten up. And have you guys seen that sheet of dance moves? It's like all the sine x, cos x, x squared, x to the 3. Yeah, the root of x. I feel like there's some yoga moves in there. You could do a whole yoga sequence. Just x squared, x to the 3. Maybe that's how I get YouTube famous.
I think so.
Step number 1, be better at yoga. I've got the functions down. All right. Let's see here. So what do we He's got some better looking ones here. Steal this one. I don't have to whisper that. He allows it. Okay. And so here, the purple one, it's kind of hard to see. The purple one is x squared. That's the one we're used to seeing, right? And then the green one is x to the power of 4. So that would be the next even power, right? And so as you can see, it's kind of sitting down on the x-axis a little bit harder and a little bit tighter around the y-axis, right? But the general behavior is the same. Now, the reason that we want to talk about that is because we're usually interested in the long run behavior, right, of the function. As x goes to infinity, what happens to y, right? Here, in this case, it looks like, well, y is going to infinity as well, positive infinity. Same thing, if x is going to negative infinity, what's happening to the outputs? The y's are also going to positive infinity again, right? As opposed to those odd functions, right? Which will go down to negative infinity. Right? So that long run behavior is what we're here for. Okay, so notice the general shape of, and this is true for any even power, is pretty well the same. For any even power is the same as f of x is equal to x squared. I'll put same in brackets, right? Some changes, but generally same shape. Okay. What do we see? We see that as x goes to infinity, f of x goes to infinity as well, right? So we're going to use that kind of notation, and it's just shorthand, right? You can write that out in words, but my wrist is killing me, and also I don't want to. because we have the shorthand, right? But so as x goes to infinity, you can write that in words if you prefer, right? F of x also goes to infinity, right? But here, this is shorthand to describe the long run behavior Same thing on the other side, right? As x goes to negative infinity, right? So now I'm heading the other way. F of x is going to positive infinity again, right? Nice. Same thing in general for the odd powers. I don't know about you. I always prefer even powers. Odd powers kind of weird me out, but I don't know. There's no explanation for that. Just is. X to the power of 3, we know what that looks like, right? All of these look generally the same. Just notice that it kind of sits on the x-axis a little bit harder, if that makes sense. Kind of plunks down, right? And then it tightens up against the y-axis, right? But the long run behavior is the same, right? And so for odd powers, as x goes to infinity, f of x is also going to go to infinity. And as x goes to negative infinity, f of x is going to go to negative infinity. So you don't need the graph to, I mean, the graph makes it easier to see, right? But now knowing that this is always the behavior of an odd power and this is always the behavior of an even power, then you can visualize the long run behavior. Okay. Okay. What if, and I didn't bring it in yet, but I will. Where is it? And I had forgotten to post it, so I posted it just this morning. The examples, let's see here. And here's the first one. Starting out with a bang. If f of x is negative 2x squared, what if we, let's do these in reverse order. Why? Because the negative flips it, right? We don't want to deal with that quite yet. How about, yeah, I'll do it like this, A and then B. It's just the morning. We haven't even warmed up yet. We can do it. It's just harder. Okay. So if g of x is 3x to the power of 3, well, I know what the power of 3 looks like. And so, right, no axis flipping here, right? And so in my mind, I just kind of visualize it, something like that. right? That's all I need to answer the question. We were just asked to describe the long run behavior. So as x goes to infinity, g of x, almost f of x, g of x is going to go to positive infinity as well. And as x goes to negative infinity, g of x is going to go to, go to negative infinity. The 3 out front doesn't impact it. It stretches it, right? Or I can never get those straight. That's why they're on your formula sheet. Stretches it, compresses it, I don't know. Right, but it's just manipulating kind of the width of this thing, right? And not the shape, right? And so, well, not the long run behavior at least. All right, so now we're ready to level up. So the 2 doesn't really do anything, but the negative does, right? And so, well, 2 does something, but not impacting the long run behavior. So let's see here. We have f of x is equal to negative 2x squared. The negative 2, do you prefer I use the formula sheet because that's what you're going to have on the test, or Desmos? You can do both. Or just one thing. So from the formula sheet, all right, we know we're multiplying the whole function, right? We're not multiplying just x. And so here, these are the only 2 negative ones, negative transformations that we have. Oh, yikes. Did something weird. In terms of identifying which one of these you should be using, right? Yes, the negative is kind of on the x a little bit, but not really. It's on the f of x. Why? Because I could divide this over and multiply it over, right? And then I would have negative f of x is 2x squared, right? What would it look like if I had a negative x instead, right? A negative x would look like 2 times negative x squared, right? And that's different, right? And so in this case, we're reflecting the graph of f of x in the x-axis, all right? And so what does that look like? So usually what I like to do in my brain is I start with x squared. I know that that's the shape that I'm dealing with, but then here, this is the x-axis, right? And so what do I need to do? I need to flip this thing on the x-axis, which makes it look like this, right? And so here, this is negative x squared, which may as well be negative 2x squared, or 3 or 4, it doesn't matter, right? But the general shape is that. Yeah? So then, oh, all right. You didn't like the graph, but I think it's still useful. Let's do 2x squared to begin with. Right. Looks like that. Great. Now, what if I make this negative 2x squared? Phew, we did it. All right, just to confirm. Yeah. So now what's the long run behavior? The long run behavior as x goes to infinity, f of x is going to go to negative infinity. None of my infinities look very good. As x goes to negative infinity, f of x is also going to go to negative infinity. Oh. Nice. Okay. Good. What if we had more than one power term? Uh-oh. Now, what are we talking about? We're talking about polynomials. Polynomials. Oh, here's a little. I'll grab this just for funsies. Bring it in there. Oh, we already talked about it. I guess I should have brought it in earlier. But I think the term long run behavior is relatively obvious. It's how it behaves in the long run. Okay. Oh, I want to use this example, which they use to introduce polynomials, because it feels very relevant to you, I guess, and the environment. Let me bring it in here. Sorry. Of course, it's stretched across pages. Oh no, we can do it. Okay. Sort of water related. It is. It's as good as it gets sometimes. An oil pipeline bursts in the Gulf of Mexico. Sounds familiar. Causing an oil slick in a roughly circular shape. The slick is currently 24 miles in radius, but that radius is increasing by 8 miles each week. Yikes. If we wanted to write a formula for the area covered by the oil slick, we could do so by composing two functions together. Oh, those function compositions. We don't like those, but we need them. First, we need a formula for the radius, right? And then, which depends on the number of weeks. And then I can put that into the area functions or function of a circle to find how quickly it's changing. Yeah. So in general, what does this look like? Well, it's always helpful to kind of draw a graph. So we're given this initial oil slick with a radius of 24 miles, right? And then we're told that the radius is increasing by, whoa, that's a terrible circle. Not much better. Increasing by 8 every week. Right? And so on and so forth. Yeah. Okay. So the radius is going to be what? Starts at 24, and then it's increasing by 8 every week, right? And so how am I going to translate that into a function? I can say that the radius, let's write it out in words first, or kind of a mix of words, and then we'll move into function notation, right? The radius is 24, and then increasing, which means plus 8 miles, 8 every week. Yeah. That's good. If I used W, let W denote a week, right? Week 1, week 2, week 3, week 4. then what do I have? Then I have the radius as a function of the weeks. Uh-oh. It's okay. All right. Because the radius depends on what week it is. All right. And then you can plug in, you can give it an input of what week you're at, right? And it'll give you the radius, right? And so that's how that function notation works. So the radius as a function of the week is 24 plus 8 times W. That looks familiar. We know what that is. That's just a linear function, right? We know how lines behave. We're pretty comfortable with lines at this point, right? Linear functions. And so now what? We didn't want the radius. We wanted to know the area. If we wanted to write a formula for the area covered by the oil slick, what's the area of a circle, right? It's moving out like this, right? The area of a circle is pi r squared. Wow, that's nice. We just found what r looks like, the radius. So the area of a circle is pi r squared. Where r is 24 plus 8w, right? R is a function of the weeks. So then pi times 24 plus 8w squared pi is just a constant, right? So that's just a number. And then 24 plus 8w squared, I'm going to have to expand that. I could leave it as is. How would I write the function notation for the area of this circle? The area is now a function of w, right? And so this is going to be the area as a function of w. Whereas here, when we just have it as pi r squared, this is the area as a function of the radius, but the radius was a function of w, right? So what did we do? This here is the same as the area composed with the radius of w. You know how to do that. Maybe not like that yet. We haven't really done anything like that. I've just given you two functions, compose these. But this is why you have to do that. Yeah. All right. What happens? The area of W is pi times 24 plus 8W. If I have to expand this, usually I just write it out twice and I visually FOIL it out, right? Because it's safer for me. But if you're really good at expanding, then go for it. But I'm not. Pi times 24 times 24, who knows? $576. 24 times 8 plus 192W, which is the same as 8 times 24. So 192W again, and then 8 times 8 is usually 64. Doesn't hurt to check. W squared. And 192, I can simplify that. 192 plus 192 is 384. So I get pi times 576 plus 384 W plus 64 W squared. Huh? I can rearrange this. Usually what we do is we rearrange with the highest to lowest powers, just in the right order. But for now, let's leave it here. Emily, you can't be serious. We just finished lines and now you're expecting me to do this? No, I'm not. But it's illustrating what? It's illustrating how we get polynomials and why we would need polynomials, because this is a polynomial. A polynomial is a bunch of power functions linked together by addition or subtraction, right? And so that's what we're going to be working with. Okay. And so, no, I'm not expecting you to go from here to here yet, but I will, or something similar. But for now, we're just introducing polynomials. All right, so let's see here. He's got a little, not so little box here that we need to work our way through. Let's see here, grab all of this. Will it fit? And is it cake? Okay. So a polynomial is, so poly means many, right? Nomials, I guess, is terms. I don't know. Numbers, I don't know. Nomial, I'll have to look that up. The etymology of these words is usually helpful, but poly means many, right? And so now I have many terms, and that's why I'm guessing that nomial means terms, right? And so now I have this link of power functions. Yeah. And so here, this is power functions added together. I'm not going to say subtracting because I think it's really important to remember that subtraction is just a special case of addition. How do you subtract something? You add the negative, right, of something. And so you can just say addition and it covers all of it. Same thing with multiplication, right? Division is just a special case of multiplication, right? So there's really only two things that you have to do. It doesn't feel like it. Okay. So we're going to have these polynomials. Now, polynomials have different little pieces, right? And so usually there's some sort of coefficient, and the coefficient that we have, we use a typically. You can use whatever you want, as long as it's not x, right? X is the variable and a is used to denote the coefficient. We've seen things like f of x is negative 2x squared, right? And so, for example, we saw f of x is negative 2x squared. That is a polynomial. It's monomial because there's only one term, right? But how can I rewrite this? I can rewrite this as f of x is 0 times x to the 0 plus 0 times x to the 1 minus 2 times x to the 2 plus 0 times x to the 3, and so on and so forth, right? All the coefficients are just 0 for everything but the x squared. And so it's still a polynomial, it's just a very boring one, right? And so now the coefficient in this case is -2. A term is if I just asked you, hey, how many terms are given here if you ignore the ... right? If you had to guess, oh, I have no idea what she means. How many terms are given? Well, 1, 2, 3, 4, right? Ignoring the ... end it there, right? And so it's exactly what you think it is. It's how many kind of chunks of power functions that you have. Right? And so any lump of a subscript I and x to the power of I, okay, we're going to use that subscript notation, right? This is just to denote that this a is linked to the power of this x. So a2 is linked to x to the power of 2, a3 is linked to x to the power of 3, and so on and so forth. A0 is linked to x to the power of 0. What's x to the power of 0? 1. Nice. Therefore, we just write A0 first, right? A subscript 0, A1, x to the power of 1, A2, x to the power of 2, A2, Emily? An x to the power of n is just the general endpoint for an nth term polynomial. Okay. And in case I know that polynomials are kind of tricky, especially when we introduce this type of notation, right? But we'll get more comfortable as we work with them. Okay, but this is the general structure of that power term, each power term. Okay. Okay. The degree of the polynomial is the highest power of the variable, so of x usually, but any variable that occurs in the polynomial. Okay, okay. That's good. So in this itty bitty example, the degree would be 2, right? Because that's the only power, so it's the highest. What about here? It's degree 2 as well, right? Because the highest power of w is 2. Why is that going to be useful, do you think? Well, it determines the long run behavior. So it's like the big brother, and it says, okay, no matter what happens here with you, little w, and you, little w to the power of 0, in the end, we're going to be doing whatever I want to do, which is b squared, right? And so, so knowing that, so when we add in more terms, things happen in the middle, but overall, the behavior is going to be the same as the highest degree or the highest power, which is why we talk about the degree of the polynomial. Now, the leading term, remember the terms are the individual power functions that are linked together in the polynomial. Now, the leading term is the term that contains the highest power. Okay? So well, this one's super boring. There's only one term, so it's also the leading term, okay? -2x squared. What about here? The leading term would be 64w squared, right? The degree is 2, yeah, but the leading term is the whole thing, 64w squared. And then the leading coefficient is, well, exactly what you think it is. It's the coefficient of the leading term. So in this case, -2, that's boring. In this case, 64. Usually what we do, because we're going to be looking for the degree of the polynomial and the leading term and the leading coefficient, usually, and because it kind of leads the way, usually what we do for polynomials is we rewrite them in decreasing order of powers, right? Just because they just kind of, the rest of them follow the highest power, okay? And so you don't have to, it's all the same, but it does make it easier when you're looking at these polynomials. And so it's just good practice, okay? So you rewrite the powers as if they're descending. So in this case, we would write it as, right, or 64w squared plus 3, oops, missing the 3, 384w plus 576. Just in decreasing powers. Okay. Let's do, hey, where did it go? Chapter. Hello? There. Sometimes it does weird stuff. Let's do an example. Find the degree, the leading term, and the leading coefficient for each of these functions. F of x, maybe I'll crop this up and do them one at a time. Split them up. Okay, first thing you want to do, right? If you're looking for the leading term and the leading coefficient and the degree, then it's super helpful if it's all just listed in descending order in terms of the powers, right? And so that's the first thing I'm going to check. Well, looks good. X to the power of 5, x to the power of 2, x to the power of 0, right? So we wanted the degree, let me bump this down. The degree of this thing is what? 5, right? Knowing that, what do you expect the end behavior to look like? It's kind of a bad one because it's also a little switcheroo, right, on the x-axis. So we know that an odd power looks like this, but now it's been switched around the x-axis. So now, right? So overall, there might be stuff going on in the middle, but overall, it'll look like that, all right? Okay. We're not quite there yet. I got carried away, but that's why we need to know the degree. And also the leading coefficient. But what's the leading term? Has to be that -3x to the 5. How many terms in f of x? 3, right? 1, 2, 3. So the leading term is -3x to the 5, and the leading coefficient is what? -3. Okay. Let's do the next one. I want the degree. Oh, there was one more thing I wanted to do here with, sorry, with this. I didn't need to erase that, I guess. Starting at x to the 5, what if I wanted you to write out all the terms down to x to the 0, right? Only because it's important to recognize that there are terms in between, right? They're all in there, but they all have a power or a coefficient of 0, right? And so this is the same as -3x to the 5 plus 0x to the 4 plus 0x to the 3 minus 3x squared plus 1 to, nope, 0 times x to the power of 1 plus 1 times x to the power of 0. I mentioned that because we're going to need to use that later when we do long division of polynomials. And I know that's something you're looking forward to. What? Long division? I know. But it's pretty fun once you get the hang of it. And it makes you look really cool. So there's that. All right. Let's do the same thing with g of x. Let's write it out. I'll start with x to the power of 4 because it's my leading term, right? And so I'll start there. There's no reason to keep going because they're all coefficients of 0 anyways. And so number one thing we do is figure out the highest power or the degree of the function. So here we've got 4x to the 4. Rewriting it in descending order. X to the 3 I have, so plus x to the 3 plus 0x squared plus 0x to the 1. Usually we don't write the 1, but it's nice to visualize it. And then plus 3x to the 0. Now we can say that the degree is 4. The leading term is 4x to the 4, and the leading coefficient must be 4. What would the long run behavior look like if you had to guess? And your guess is going to be pretty good. Well, I've got an even degree, right? So overall, it's going to look something like this. It's got a positive leading coefficient, so it stays upright, right? There's no flip. And so now this is going to be the long run behavior of this thing, right? The x to the 3 does a little activity in the middle that we'll deal with, but overall the long run behavior is going to be that of x to the 4. Okay. Whew. Not on the test. Test 2, yes. So you have something to look forward to. Okay. Let's see here. Did I? Okay. I think he's got a. He's got a little thing. We've already said it. But for any polynomial, I'll highlight any. it's true. The long run behavior of the polynomial will match the long run behavior of the leading term, right? And so that's what we've already sort of introduced, right? But here it is as a fact in a box. Oh yeah. Let's do another example. Oops. If we have to describe the long run behavior of each of these, what's the first thing that we would have to do then? We would have to figure out what the degree is and also what the leading term is, right? And so number one thing is you're going to sort through this polynomial, and it's always nice to rewrite it in descending order if you have to, right? But in this case, it already is, so I'm happy, right? As an exercise, you could rewrite it with all the terms, even with the coefficients of 0, but it would just look like this, right? So the leading term in this case is 3x squared, which means that the degree is 2, right? It's positive. And so here it's going to look something like this, right? Which means that as x goes to infinity, f of x is also going to infinity. And as x goes to negative infinity, f of x is going to positive infinity. Guess we've already seen these. This one's a little sneaky, right? Again, I'll put it over here. The leading term is negative 2x to the 3, but it's going to have the overall behavior of the leading term. And so that negative is going to do the flip. Now, I like to always just think about my base function, that toolkit function, x to the power of 3, which I know what it looks like. And then I flip it on the x-axis, and I end up with something like that, right? And so here I have negative x to the 3. And the 2 just kind of makes it squishier. And so knowing that, I can say that as x goes to positive infinity, what's going to happen? So x is going to positive infinity. So this thing's going to negative infinity. Or g of x is going to negative infinity. And as x goes to negative infinity, this thing is going up to positive infinity. What if we had something like this? Looks terrible. But if I have to determine the long run behavior of this thing, what do I need to do? I don't need to expand it, although you could. That's a safe way to do it, but it's very tedious, right? What are you looking for? You're looking for the highest power of x, and then whether it's going to be flipped on the x-axis or not, right? And that's really all you're interested in. So, okay, if I think about this term, this one's a pickle, right? Because I've got the square on the outside. So this is really x minus 1 times x minus 1 if I wanted to rewrite it, right? And so here I can rewrite h of x is -2 times x minus 3 times x plus 4 times x minus 1 times x minus 1. What's your highest power of x? You don't have to expand it. Yeah, nice. So, but if you kind of imagine expanding it, right, you would end up with x to the power of 4 as your highest power. Right? And so x to the power of 4 is the highest power. So therefore, the degree is 4. We need the long run behavior of this thing, which means that we need the entire leading term. Now, if you expanded this out, you would end up with just an x to the power of 4 because there are no coefficients on these x's, I guess. And so the leading term would be -2x to the power of 4, right? And so here, the leading term would be -2x to the power of 4. Right. And if that's not obvious to you, then I encourage you to FOIL this out, right? Just working methodically and expand 2 sets of brackets at one time, right? Leaving the others alone, and then slowly work your way through the brackets, right? But it's going to be very tedious, and but it'll always work, right? That's usually how these things go. So what's the long run behavior of this thing? -2, so the negative takes the x to the power of 4, which looks like a parabola. Boop. But then I have a little flip here. So I have -x to the power of 4, which means that as x goes to infinity, h of x is going to go to -infinity. And as x goes to -infinity, h of x is going to go to -infinity again. Good. Okay. So once you've expanded this, there is going to be activity in the middle, right? We've talked about the long run behavior, but there is going to be activity in the middle that kind of makes this thing look weird. And so let's see, maybe this one's a little bit too. All right, I'm going to graph it. Do I have it here? 2x minus 3x plus 4x minus 1, just so you can see what it looks like. -2, and I'm just going to type it in exactly as it's shown. X minus 3 times x plus 4 times x minus 1 squared. Whoa. So we really nailed it on the long run behavior, but we have to zoom out quite a bit, and now it's hard to see. But here, right, so there's some activity in the middle, but then overall, if I zoom in here, then we have that long run behavior. But what's going on in the middle, right? That's what the other terms are telling us. Okay, and so you can graph them, right? But sometimes it's hard to visualize, I think, at least in my brain. So what we want to do is, was there anything here that I wanted? I feel like there was. I think it was this that I wanted to bring in. Oops, I hope I copied it. Yeah. So now for the short run behavior, okay, we're gonna have things like vertical and horizontal intercepts, and places where this graph changes direction, right? We saw in this graph, it's hard to see, right? But we can talk about this first change in direction, right? And then it drops down, and then it shoots up, and then it drops down, and then it keeps going to infinity, or negative infinity in this case, right? And so that's the short run behavior of a polynomial. Okay? So some of the things that we want to talk about are the vertical and the horizontal intercepts. Just as a side note, it's good that he mentioned it because sometimes I forget to. He mentioned it, David Lipman. I guess, and Melanie Rasmussen. But less familiar. So just as a side note, horizontal intercepts are what? They're on the x-axis, right? And so here, when we're crossing the x-axis, those are horizontal intercepts. Horizontal intercepts, but also you could call them zeros or roots of the function. So same thing, but just three different terms that mean the same thing, where it crosses the x-axis. Crossing the x-axis is going to mean what? It's going to mean that the function itself, the output is 0, right? And so a function f of x crosses the x-axis when f of x is equal to 0. Right? So when the output is 0, that's when you have these horizontal intercepts or zeros or roots. They're going to be more interesting than the vertical the vertical intercept. The vertical intercept is where it crosses the y-axis. When does that happen? That's at f of 0, right? When x is 0, that's when it crosses the y-axis. So f of 0. Okay. So you plug in x equals 0 and you get the output, and that's the vertical intercept. That one is pretty straightforward typically, but this one is a little bit more of a thinker, right? What values of x give me an output of 0? Okay. We would need to find what values of x produce an output of 0. Starting off nice and slow, but also let me just see if he has a little handy. Not yet. Something to look forward to. Here, butter there. Find the horizontal and vertical intercepts of g of x is 2 times x minus 1 times x plus 3 times x minus 2. Now, when it's factored like this, it's super helpful, right? And so if it's not given to you in factored form, it's always worthwhile trying to put it into factored form, breaking it up and representing it like this, okay? But let's start with the vertical intercepts, right? The vertical intercept, we said, was just evaluate the function, or I guess it's a g, doesn't matter. But I don't want to be confusing, more confusing than I have to be. G of 0. Hey, how come no one stopped me? It's game over. Try this on your own and we'll pick up here on Friday, I guess. Wow, have fun with that. Let me just write out here. This is where g of x is equal to 0. There. Try that on your own, but study for the test first, okay? All right. If you have any questions, let me know. Otherwise, I'll see you in the B building for test number 1 on Wednesday.